a series on protection technology. These 3 Siemens Power Academy lectures are designed for those who want to expand their knowledge and understanding of relay protection for distribution and transmission grids. Today we will focus on DC components and current transformer dimensioning rules, mainly for professionals from distribution and transmission grids. We will record the webinar and make the recording and the slides available to all participants. Please type your questions in the Q&A field. We will answer these during the dedicated Q&A session after this series. And now let me hand over to our expert Siegfried Lemmer. The stage is yours.
We also have to look at DC components, because in many cases at fault inception we have DC components on the short circuit current, and you will see now in the following simulations that these DC components significantly influence the saturation behavior of the current transformer. In this picture you see again the simulation of the point where the saturation starts, and I will now change the conditions a bit. I will reduce the current. You see here we have 20 amps. I will reduce the current to 10 amps, and I will also reduce the burden from 15 ohms to 6 ohms. And that means we are now far away from the saturation point. We have reduced the current from 20 to 10 amps, and we have reduced the burden from 15 VA to 6 VA. That means we are far away from the saturation point. And of course everything is fine, no saturation visible. And now if you look down here, there are 2 sliders I have not used up to now, and one slider is the fault inception angle. The fault inception angle influences the amount of DC component on it. And up to now in the simulation, the fault inception angle was always so that we had no DC components on it. It's the most likely case, because in most network it means we have the fault inception at the voltage maximum. That is the point where faults most likely starts, but not in all cases. Well, for instance, if you damage a cable by street work, it's a random thing where the fault starts. So there is always a possibility that the fault inception angle differs from this value and you get a DC component on it. And look what happens if we change the fault inception angle and get a DC component. Now I am around 60 degrees. And what you see now is we have significant saturation, although we are significantly below the saturation point. And this saturation comes from the DC component. Look, the 0 point is here. That means the first periods we have a strong DC, a full DC on the short circuit current. And this DC drives the current transformer into saturation. And that is a thing where we have to look at very carefully. We can increase it even more if we increase the phase angle here, but you see the effect is there. And that is of course a thing which has to be considered, because these DC components may happen. Now, of course, it's interesting, what would our algorithms say on that? Remember, we have 10 amps currents, so they should measure 10 amps. And now I can activate the algorithms. And what you see here, now the dashed lines again, you see the green result. That means that is the algorithm applied to the original value, measures something around 10 amps. So we have a slight oscillation on it. That is because of the DC component that disturbs the Fourier algorithm a bit. And if we look at that result based on that what our protection relay measures, that looks really strange. So it goes up. At the beginning it measures really something around 10 amps, but then it goes down, and from these disturbed quantity it measures something like 4 amp, 5 amp. And what would that mean? Imagine you could have a setting maybe in our protection relay of 5 amp. You have 10 amp short circuit current. You would expect tripping. And there are now two possibilities. Either you trip already here in the beginning. There we have enough current to trip with this 10 amps. But if we have a delay, trip delay, here it would not trip with a setting of 5 amp, and you see the DC component disappears slightly, in this case with a pretty long time constant, and for that reason this calculated current, that what the algorithm in a protection relay would calculate, that starts to increase, and after some 100 milliseconds it will be around 10 amps again, when the DC component has disappeared. That, of course, is a thing which doesn't really look nice. I must confess, this is really an extreme case. You see here I have a time constant of 200 milliseconds. That is the time constant of the short circuit loop we have. And that means we must now ask ourselves the question, what are typical time constants we can have in our networks? For that reason, we have to calculate the impedance of the short circuit loop in case of a short circuit. Theoretically, that's quite a complicated thing, because if we have a short circuit somewhere in the network, the current comes from a lot of generators through a lot of transformers and cables to the short circuit point. And now calculating that impedance by hand is pretty complicated, but we can do a few estimations. If we are, for instance, inside a medium voltage cable system, away from transformers, just in the system, and then calculate the short circuit loop impedance, this is in these cases mainly defined by the impedance of the cables behind us, the cables which limit the short circuit current. And a time constant of a cable impedance, that is always the inductance divided by the resistance of a cable. The time constant of a cable is something typically maybe around 5, 6, 7 to 10 milliseconds. That means a much lower value than what I used in the simulations. And we can see what happens. You see here with 200 milliseconds, we get severe saturation. If we now simulate the same thing just inside a cable system, maybe I take 7 milliseconds, then you see the DC component disappears within pretty short time. It's only there for the first half period and then it's more or less gone. And that means, in this case, luckily we can forget the problems with saturation generated by DC components, if we have these time constants. If we go into a transmission system, again, we have a short circuit and a location which is away from feeding transformers. We may have time constants around 40, maybe 30, 40 milliseconds. Then it looks in this case, already a bit different. Then you see with 40 milliseconds, it takes a bit more time until the DC component is gone. That means we have a few half periods with significant saturation, and then it disappears again. So there it's a bit worse than in a cable system, and especially in transmission systems, time delays resulting from such a thing are not good, so they have to be avoided. So we have to look at saturation stimulated by DC components a bit more. And now you may ask the question, yeah, why did you choose 200 milliseconds? Because if we have 9 in cables and maybe 40 in overhead lines, the problems there are generators and transformers. If you are, for instance, in a medium voltage system, just on the medium voltage side of a transformer and make a short circuit there, or if you are in a transmission system close to a power station where you have the unit transformer and make a short circuit there, then the short circuit current is mainly limited by the transformer reactance or the transformer impedance. And transformer impedances or generator impedances, they have a long time constant. And there you may end up in 200 milliseconds or even more. And that means also in medium voltage installations, you may get things like I showed in the beginning with long time constants and saturation stimulated by DC components. So that means these things become more critical or most critical if you are in a network close to a transformer or to a generator. So that was the simulation. Let's summarize this a little bit on a slide. Yeah, in this summary you see again the curves without saturation. Primary, secondary current have identical shape. Magnetizing current can be neglected. And if we have saturation stimulated by a DC component, you see here this curve has a significant DC component, a full DC component. You see at the beginning we have nearly no zero crossings, and that causes severe saturation, especially if the time constant is very long. Okay, let's summarize that what we found out in these simulations. Current transformer saturation may disturb the measurement of the currents. If we have saturation, our protection relay receive disturbed current curves, and with these current curves, the algorithm, it depends a bit on the algorithm, they typically underestimate the currents. And if we have DC components, especially if these DC components have long time constants, this may significantly increase the saturation effects. That means even in cases where we don't have or where we wouldn't expect saturation, we can see suddenly saturation effects. So what does that mean? Is that dangerous? I already mentioned a few cases where we see, okay, it's not good. What can happen in protection if we underestimate the currents? Let's look at overcurrent protection. If an overcurrent protection relay underestimates the current, we can have the case that it underestimates it in a way that it sees suddenly a current below the setting value, although in reality the current is above the setting value, so there is a risk of a missing trip. If the setting comes from DC component, the good thing is, that means if we have no saturation steady state, saturation only coming from a DC component, then the good thing is that effect will disappear. That means after some time the measurement will be correct and we will have a correct trip. But we must keep in mind there is a certain risk of underestimation of the current, of a missing or a delayed trip. The same applies to distance protection. Distance protection calculates the impedance, that means voltage divided by current. If the current is underestimated, the impedance becomes higher, and that means if we have a fault, a short circuit on a line, we would expect that the measured impedance is inside the zone 1 of a protection relay. If we underestimate the current, impedance becomes bigger, it can move us out. If it is a temporary effect only, it may move in. And imagine, or remember, when I showed the saturation effects stimulated by DC, you saw in the beginning, in the first 10 milliseconds, it looked pretty fine and saturation only began after that. That means always in the beginning of the short circuit, just after fault inception, you have a certain time span where there is typically no saturation. And if you design a distance relay, for instance, you may have to look at that point and may try to use that point for a fast, or that interval, measurements from that interval for a fast trip. But theoretically, you have always a risk of a missing or a delayed trip. You have typically no risk of a wrong trip. There are theoretical cases where you even can have a wrong trip, but normally it's a missing trip. More critical is the differential protection. Imagine a line differential protection, and there the critical case is not tripping for a fault. The critical case for differential protection is not to trip in case the fault is on the next line. Imagine you have a line with it protected by a differential protection, and you have a short circuit on the next line. That means the protection of the next line should trip, but your protection of the healthy line should not trip. But your protection will now see a strong current flowing through the line, inside on one side and out of the line on the other side. That means both current transformers of the line will measure a pretty high current. But they are identical, the difference is zero, the protection will not trip. If now both current transformers go into saturation, still no problem, because if the saturation is identical on both sides, still no current difference, still no trip. But if the current transformers are of different design or different dimensioning, you may have saturation on one side and no saturation on other side, and then you may see a differential current and you may trip, although the fault is on the next line and not on your own line. That means for differential protection, there is also a risk of a wrong trip. And that is a point where people become more careful, especially in medium voltage. You may be willing to accept some little bit delayed trip, but a wrong trip typically causes trouble. That means we have to figure out how is saturation determined. And what we learned up to now, of course, the short circuit current determines the degree of saturation. That means the magnitude of the current and DC component, the time constant and the amount of DC component. Then, of course, the rating of the current transformer. What is the nominal current? What is the rated power? And there already the discussion begins, because a bigger current transformer reduces the risk. A current transformer with a higher rating reduces the risk of saturation, but is more expensive. That means you end up in a discussion between cost of a current transformer and saturation, which is a nice discussion maybe with your project controller. And then, of course, the type of current transformers. Remember, we have different classes there. And, of course, also the burden. So you see there are a lot of parameters influencing the thing. If you want to simulate that, you have to solve differential equation, what we did. And you also, if you want to simulate the behavior of a protection relay, even if you manage to simulate the disturbed curves, you have to know how does the protection relay work. And in a protection relay, you have typically not one algorithm and the manufacturer doesn't want to tell it to you. No, that's not the issue. The issue is normally in a modern protection relay, especially in a distance protection relay, you have some adaptive algorithms. That means you have algorithms who can be fast if possible, or who are slower if they have to be more accurate. So there is not one algorithm. So you see the whole story becomes complicated. You don't want to do simulations for every stupid medium voltage current transformer. So what can we do? And the solution for that is the manufacturers of protection relays have to publish dimensioning rules for CTs. That means they have to publish rules, and if you as a user observe these rules when you engineer your substation, then the manufacturer guarantees that the whole story works. And defining these rules should be easy. Should be rules. I will show some examples later on. These rules should be usable without solving nonlinear differential equations. They should be checked by simple head calculation or maximum a pocket calculator. It's a bit work on the manufacturer side, of course, because you have to change all these parameters there, and you have to check your rules against variation of all these parameters. And remember what I told you in the beginning about the P-class current transformer. That are the current transformers who are the majority of current transformers in the field. These current transformers have no defined behavior concerning the transients. That means we must test the protection relays against saturation effect where the behavior is not really standardized. That means we have to assume, based on field experience, how would the current transformers behave there. But this story has a long tradition. That means the manufacturers have collected a lot of experience, and experience says if you observe these rules, it will work. And now I would like to show how these rules look like. That means I will make two examples for the dimensioning rules. These examples will use P-class current transformers. As I said, if you look into our manuals, you find dimensioning rules also for the other classes. And in order not to extend this video by many hours, I just restrict this to P-class current transformers. And in P-class current transformers, the dimensioning rules are based on the so-called accuracy limiting factor, ALF. And the ALF is the rated accuracy limiting factor. Remember our 5P20 current transformer we had? The 20 in this class designation is the ALF. And the definition is that the current transformer can measure a current up to ALF times rated current. That means 20 times nominal current in our example, within its defined accuracy limits without significant saturation if the burden is the nominal burden. We can again show this example. Our example current transformer, 15 amp to 1 amp, 5P20, 15 VA burden. This 5 means that the accuracy limit is plus minus 5%. You find also other current transformers, maybe 10 there. In our example, it's 5. And then the 20 is the ALF, the rated accuracy limiting factor. And you have there the burden, 15 VA, as it is 1 amp rated current on the secondary side. That means the rated burden in ohms is 15 ohms. And now if we do the dimensioning, we have to take into account that the actual burden we have may be lower. What you, for instance, sometimes have is you have a very old current transformer which was at the beginning of his life still connected to an electromechanical distance relay, which had a pretty high burden, because these old things, they had to take energy from the current transformer for operation. They tend to have a high burden. And if you now connect there a digital relay, these relays have a burden which can nearly be neglected, but you always have to take into account the wiring between the CT and the protection relay. And if you have an outdoor substation, this wiring may be pretty long. But you may end up in a burden which is lower than the nominal or the rated burden. And for that reason, we define this ALF dash, this operational accuracy limiting factor or effective accuracy limiting factor. That is the current which can be measured without significant saturation, taking into account the actual burden. And this can be calculated from the rated accuracy limiting factor by this formula. You take the rated accuracy limiting factor and multiply it by this ratio, which takes into account how much the actual burden differs from the rated burden. And in our case, it would like this. If we, for instance, assume a rated burden of 2 ohms, an actual burden of 2 ohms, the effective or operational accuracy limiting factor is 20. That is the rated accuracy limiting factor, multiplied by this ratio between winding resistance plus nominal or rated burden, divided through winding resistance plus actual burden, and in our case the result is 72. That means if we run our current transformer, which has the saturation point by rated burden at 20 times nominal current, if we run this current transformer with the reduced burden of only 2 ohms, we can measure steady state 72 times nominal current without significant saturation. And this is used also for the dimensioning rules, as you will see on the next slides. The first example is an easy one. That is one for an overcurrent protection. In this case, I take 7SJ82, and we assume that we have an application where there is a setting of 15 times nominal current, so it's a pretty high current value. And in this case, we have a current transformer. You see it's a smaller one, 5P10. That means the rated accuracy limiting factor is 10 and only 5 VA. And we assume that this CT has a winding ratio of 3 ohms, and we assume that our actual burden is pretty low, only 0.6 ohms. That is a typical case if you are in an indoor medium voltage substation. You have the relay installed just on the low voltage compartment of the switchgear. That means the wiring between the relay and the current transformer down in the switchgear is pretty short. That means you only have the internal burden of the protection relay, which is pretty small, and this small piece of wires between protection relay and current transformer. That is why we have this relatively low burden. Now you take the manual of the 7SJ82, look into the table of contents. It's thick, the manual, I know, but the table of contents shows you somewhere you find the dimensioning rules. You find dimensioning rules for the different classes of current transformers. You look what the P class says, and there you find this table. And this table defines the required minimum effective accuracy limiting factor. And it says, unfortunately here it is called KALF dash. It says it must be the setting defined by rated current. In our case, the setting is 15 times nominal current. So this would say the minimum KALF dash is 15, but then there's an additional sentence. It says, but at least 20. That means as long as the setting is lower than 50, the requirement, and that is a very simple requirement, the requirement is KALF must be more than 20. That means you take this 20. That means from that you get the information. The 7SJ82 requires that you have a current transformer where the ALF dash, the effective or operational accuracy limiting factor, is higher than 20. So now it's pretty easy. We take these values and calculate the ALF dash as we did it on the previous slide. In our example, the ALF dash is rated accuracy limiting factor is 10. We get that from the 5P10. And then we multiply that by the ratio winding resistance plus rated burden is 5 plus 3 divided by winding resistance plus active burden 3 plus 0.6. That means 10 multiplied by 2.22. That means as a result we get, if we use this current transformer with this burden, we have an effective or operational accuracy limiting factor of 22.2. The requirement was more than 20. 22.2 is higher than 20. So it's fine. The protection will work, and you can forget all these discussions about DC components and things like that. That was an example for overcurrent protection. If we now come into the transmission level, it becomes a bit more complicated. My second example refers to the 7SL87. That is a combined distance and differential relays. That means we have two main protection functions in there, a distance protection and a line differential protection. And that means we must check the current transformer requirement for both protection functions separately. I will restrict that to the distance protection only. And additionally, the dimensioning rules for distance protection and for differential protection, they are a bit more complicated than for the overcurrent protection, because for a distance protection, you have to check two cases. On one hand, there is a requirement for a close-in fault. The close-in fault is just in front of the relay at the beginning of the protected line. In this case, you typically have the highest currents because there is no limiting impedance in the line. You have the highest current. That means you get the highest degree of saturation. But on the other hand, the measurement, there is no need for a very accurate measurement. You just have to trip and that's it. You don't need to be very accurate in the measurement. So that is one case. There it has to be checked, will the relay trip even if we have saturation? And the other thing is we consider a fault at the zone limit. And there the relay has to decide, is the fault inside the zone? It has to trip. Or is the fault outside the zone? No trip. That means there the current is lower. That means normally also the degree of saturation is lower, but the measurement must be more accurate. That means the algorithms will not accept that much disturbance of the curve. So these 2 points have to be checked. For line differential, it's a similar story. On one hand, we have to check, will it trip for an internal fault, which is normally not the critical thing. And the other thing is we have to check for an external fault. That means this example I already discussed. We have a current flowing through our line. Fault is on the next line, and we have to check, will the differential protection really be stable? I will do the calculation now only for the distance protection. You see the equations are pretty much similar, so there is no there are no other ways of calculation. What you also see is in these equations for the distance protection, you see factors A and B, and these factors have to be taken from the diagram, which is shown right off the table. It's also an extract from the manual. This diagram gives you the applicable factors based on the time constant you have. Remember, the time constant defines the saturation stimulated by DC components. That means you must know the time constant of the short circuit current, and then from this diagram you can get the factors A and B. A is the dashed line and B is the full line. So if we want to check these requirements, of course, we must know the short circuit currents. That means we must go to our friends from network planning or operational department or whoever who knows the short circuit calculation. And we assume that they did a short circuit calculation for both locations. For the close-in fault, the result was 15 kiloamps short circuit current. And the good thing is, our friend from the planning department also gave us the time constant of the short circuit current, because we need that. And if we simulate a short circuit current at the zone limit, we have in this case 6.3 kiloamp. The time constant is a bit lower, in this case 56 milliamps, because we have the line impedance in between. The current transformer in this case is a 1000 amp to 5 amp. In this case 5 amp rated secondary current, and it's a 5P30, 5 plus minus 5%, P class at 30 times nominal current with rated burden of 30 VA, and the actual burden is 0.547 ohms, and the winding resistance of the current transformer is 0.1 ohm. And with these values we can check the requirements. The first thing we have to do is we have to calculate for this current transformer the effective or operational accuracy limiting factor. We did that already several times, so it's easy. The only thing you have to take into account here, this is a 5 amp CT, and for a 5 amp CT the burden in VA does not have the identical value as the burden in ohms. That means you have to divide by 5 square, that means 25. That means in this equation, at the point where you have to input the rated burden, don't take 30 because you have 30 VA, it's 30 divided by 25. That is why we have the 1.2 there. So we end up in an operational accuracy limiting factor of 60. That is what we have with this current transformer. And now we check what is the requirement. And there we have to consider the two cases, the close-in fault and the fault at the zone limit. Let's first of all look at the close-in fault. The requirement says it is, if you look into the table, effective accuracy limiting factor must be bigger than A multiplied by the short circuit current divided by the rated current. If we go into our diagram with the 90 milliseconds, we find that the factor A should be set to 4. So we have a 4 there. The short circuit current is 15 kiloamp. The rated primary current of the current transformer is 1 kiloamp. So we have 4 multiplied by 15 kA divided by 1 kA. It is 60. That means the requirement for the first requirement for the distance protection means accuracy limiting factor, effective accuracy limiting factor should be more than 60. We just calculated, it is 60.3, so we are just okay. It's just above the limit, so dimensioning is okay. We can also check the second limit. So this is fine. We can also check the second limit. Similar formula, but now we have to take the short circuit current at the zone limit, which is 6.3 kA. And we have to take the factor B from this diagram with the different time constant of 56 milliseconds. And we get a requirement, we get a result that the ALF dash, the operational accuracy limiting factor, should be more than 31.5. It is 60.3, so this requirement is also okay. That means with these calculations we have checked that the distance protection will work properly in that application without doing any simulations, complicated differential equations and so on. So that is the way how it works. And with that we are through the examples. There is one remaining point I would like to discuss before we are through, and that is the remanence in CT. I already mentioned it in the beginning. What is the effect of remanence? Remanence means if there is no primary current flowing, we have a remanent flux in the core, and the level of this and also the sign depends somehow on the history, what happened before to this current transformer. And the problem with that is, if there is already a significant remanence and then we have a short circuit, then it means the margin we have before we reach saturation becomes smaller. It can also become bigger if remanence goes in the other direction. But there is a certain risk that we get faster saturation. What unfortunately also has been found out is that modern cores have typically higher remanence levels. So remember, this remanence level is not defined for mini classes, so you don't find it in the data sheet. That is an investigation which has been done on the ISC level, and it comes from the manufacturer of CTs, of course, had modern core material that did some optimizations, and the result was that typically the remanence levels are higher. What does that mean? The good thing is that this influence of remanence is limited to the first half cycle only. That means if we have a core with remanence, and now this core sees suddenly a short circuit current, there is a certain risk that it goes faster into saturation. That means the time before it reaches saturation can be shorter. It can also be longer, but there is a risk that it is shorter. But then, after that, there's no influence. So the influence is only in the first half period. And in the dependability case, that means in the question, will the relay trip? The only risk from that is that we may have a slightly delayed trip. That means for distance protection, for overcurrent protection, this thing is not really a critical thing. But remember, for differential protection, we also have a risk of a wrong operation. That means we have to discuss the the security case. And that means for differential protection applications, you should pay more attention to the remanence issue in current transformers. And for that reason, you also find additional recommendations in our manual. One thing you can do, if you have the possibility, is to use current transformers of these classes, PR, PXR, or TPY, that are classes where the core is split and the remanence is significantly reduced. So typically you can have remanence levels of maybe 85% or even more of the saturation level. That means you go very quickly into saturation. And these cores have remanence levels which are, I don't know, around 10% or even lower. If you have the possibility to choose such a core, of course that's only possible if you are building a new substation, if you don't have to adapt to an existing current transformers. And if that is not possible, then we recommend to use an additional overdimensioning factor in conjunction with differential protection. That means you bring into this calculation an additional factor which leads to a bigger dimensioned current transformer to avoid overfunctionality in case of remanence. Of course, that is a little bit a risk evaluation, because remanence may only make trouble if you have a high current, maximum short circuit current, if you have a high DC component, which increases the risk of saturation, and if you have a remanence, also a full remanence to the wrong side. So a lot of cases must come together, which can cause then a wrong operation if you don't consider these requirements. So I think there are many applications in operation worldwide where this has not been considered, but you may have peace of mind for 10 years and then suddenly something happens. You have a fault with a high current in a critical position, and then you start calculating and you find out, it seems to be a remanence issue. So it's worth looking after this topic already when you design a substation and dimension the current transformer. But in general, you can say these complicated things I discussed today can be mostly ignored if you stick to the dimensioning rules. These dimensioning rules have to be observed, and then the manufacturers guarantee that the protection works correctly. Thank you for listening.
Dear audience, if you're interested in more detailed information and practical training, please visit our training platform at Siemens Power Academy. I am confident you will find the right resources and training there. A link to the recording and the slides will be sent to all participants. Thank you for your active participation. I look forward to meeting you soon. Stay safe and take care. Goodbye.